Okay, good morning, everyone. Welcome to lecture 39. So we will continue with some inequalities. Last time we saw some inequalities. So we have seen union bounds, we have seen Markov inequality, and then we have seen Chebyshev inequality. And today we will talk about some more inequalities. So but to do that, I need to define something called a convex function here. A function g from some domain I to real is convex if for any 2 points x and y in I and any alpha in 0, 1, we have the following, where g of alpha x plus 1 minus alpha y is less than equal to alpha g of x plus 1 minus alpha g of y. Okay, so this g is some function here, and it is defined to be convex if it satisfies this inequality. Okay, so we will try to get an intuition behind this. So if the above inequality is greater than equal to instead of less than equal to, then we say that the function g is concave. Okay, so there are two things, convex and concave. Here alpha x plus 1 minus alpha y is the weighted average of x and y. So it's a weighted average because alpha is between 0 and 1. And yeah, so this can be seen as weighted. These are special weights because they are between 0 and 1. So you can think of these as the average of weighted average of x and y. Here, yeah, I'm seeing the same thing here. Okay, I don't know why. Oh no, okay, so here, no, not the same thing, it's different. So here alpha gx, here's gx, right? Here it was x. And then on the right hand side, we see that we have gx and gy. And then we are taking alpha of gx and 1 minus alpha of gy. So it seems that the right hand side is the average of gx and gy. Okay, there is a mistake here. So the right hand side is an average of weighted average of gx and gy, and the left hand side is the weighted average of x and y. Okay, so what does average mean in the random variable case? They are like expectation, right? So if I see g of x as some random variable, or the function of random variable, g of y also as function of random variable, which itself is a random variable, then it seems like I'm taking an expectation of g of x here. And here it seems like I'm taking g of expectation of the random variable that takes value x and y. Okay, so this is how we can visualize this. Okay, so we can assume that x is a random variable that takes value, let us say x and y. Okay, and then g of x will take values g of x and g of y. Then in terms of the expectation, what we are trying to say is the weighted average of this. In other words, g of expectation of x. Okay, g of expectation of x is less than equal to expectation of g of x. Okay, so this is what it means. So basically you already know what this inequality is going to tell you. Okay, so this inequality follows because of the behavior of the functions, because g being convex, and then if I apply the expectation on the both sides, then yeah, so I mean not really expectation on the both sides, but I see this as an these weighted average as expectation. Okay, so and same here, then I can write this. Okay, so and this will hold only for convex function, obviously, because only for convex function you have this relationship. Now let us see what it means by convex function. So there is a plot here. Now you can see from the plot, this is the convex case, and you can see from the plot that this is the condition that convex function is supposed to satisfy. So what does this mean, right? So what does this mean, right? Alpha x plus 1 minus alpha y, and this is like true for all alpha, right? So this is true for all alpha. So first of all, let us see what this means, right? Alpha x plus 1 minus alpha y, right? So alpha x plus 1 minus alpha y, and this is for alpha in 0, 1. Okay, so this seems to be a parametric equation of a line, right? And joining 2 points, right? Because if alpha is 0, then you are at y, right? So let us say this point is z. So we can treat this as parametric equation of a line. So I can write this as z of alpha, okay? Because x and y, let us say we fix x and y. Then if alpha is equal to 0, then this implies your initial point. If you assume 0 is the initial point, then it is y. And if alpha is 1, then this implies that z of 1 is x. And for intermediate values between, let us say, half, then you will be at half, right? So if alpha is half, then this implies z half will be x plus y by 2, which is the midpoint of x and y, midpoint of the line joining x and y, right? So these are the conclusions we make. So in other words, if I vary alpha continuously between 0 and 1, I will get a line joining x and y. So this is the line joining x and y, and some arbitrary point here is my zt, the z alpha, I mean, okay, z alpha. So by different values of alpha, I get this. Now, taking a g of that, what would it mean? Okay, so assuming that it's a continuous function as well. Okay, so so taking g for those values between x and y, right? So if we do that, then we get the curve values, which is this guy. Okay, so these are the points. Let us say g of z of alpha. Okay, these are the arbitrary points that I get. So g of z of alpha will be somewhere here. Okay, so and then if I vary x and y, then I get these curve values. And then similarly, if I look at this point, now g of x is this guy, right? So g of x is somewhere here. So this is g of x, right? And then this is g of y. Then what does this say, right? So this says the line joining gx and gy. Okay, so you can treat this as a like some vector point. Okay, so this is like some vector in the space, and then if I am joining these two, okay, so then it will give me the line joining gx and gy. Okay, so so what it means now geometrically is that any 2 points, right? So the x and y were also any 2 points. So if you take any 2 points x and y, and if the line joining the points gx and gy is above, okay, so this greater than equal to means that it's above the curve value itself, okay, on those points between x and y, then it's a convex function. Okay, so this puts a restriction on convex function to be a bowl shaped always. Okay, so it should be always like this. So convex functions will look always like this. Okay, so but this is not a convex function, obviously, because the line joining 2 points here is below the curve value. Okay, so that's why it's not a convex function. Okay, and then similarly, but in some places it's okay. So for example, line joining these 2 points is always is above this, but this should have been true for all x and y, but for this x and y it was not true. So that's why we claim that this is not convex. Okay, but if it so happens that the line joining x and y is always below the curve value, then there is another term that's called concave. The reason why concave is also interesting for us is because negative of the concave will be convex. So you don't really need this. So negative of concave is convex. Okay, so in general, you will see people always using convex because concave can be made convex by doing a negative of the function. Okay, but nevertheless, you also have concave and so on. Okay, if you studied physics, then you have seen the lens and so on, right? Concave and convex and so on. So so here in terms of maths, this is what it looks like, geometrical intuition. And with regard to the probability that we are studying, the expectation, I mean, the statistical properties of such functions are that the g of the expectation is less than equal to expectation of the g. Okay, that's what we will try to conclude from here. So from the definition of the concavity on the left, okay, that's what we will. So I've just revert this. I've written this guy as the first term here now, and this, the left term is the second, and then this is the greater than equal to. So for convex, this is what we are expecting. Expectation of the g of x is greater than equal to g of expectation of x. Okay, so a usual property of convex function now can be written like this. Okay. So Jensen's inequality is the following now. So gx is a convex function on some range, and expectation of g of x and g of expectation of x are finite, because then we are able to compare things. Okay, we cannot compare infinity, less than infinity, those things. So that's why we don't discard those values. So we assume only finite values are there. Then this is what we mentioned previously. So to know whether a function is convex, what do we need, right? So the first thing is that how do we know whether a function is convex? Well, we know this from the second derivative test. So a useful method is, especially if the function is differentiable function, then we apply so-called second derivative test. And the second derivative test suggests the following: a twice differentiable function g is convex if and only if g prime x, the double derivative of g, is greater than equal to 0 for all x in the domain. For example, g of x is equal to x square is convex because if I apply the second derivative test, so the first derivative is 2x, and then the second derivative is 2, and this is greater than 0 for all x in R. Okay, so this implies g is convex. Okay, so that double derivative being greater than 0 ensures that it will always remain a ball shaped. In other words, it will never bend down. It will always bend up. Okay, the rate of change of tangent always has to be in the increasing mode. Okay, or non-decreasing mode. Okay, so this ensures that it's convex. Okay, so that was our thing. So to be sure about applying the Jensen, first we need to know whether the function is convex. Okay, it has to be differentiable. I mean, what you know so far about convexity is the second derivative test. There are also other type of tests that I usually teach in the convex in the topics in applied optimization elective course. So you are welcome to explore these things in the elective. But right now, let us assume what you know from the higher secondary school is second derivative test. Okay, and this is easy enough if the function is differentiable. There are first order test also that can be applied to check convexity, but we don't have to do that yet. Okay, so okay, so this is what will help us to determine whether the function is convex if it's twice differentiable. So let us see some applications of Jensen's inequality. Consider a random variable x with expectation is 10 and x being positive. Estimate the following quantities. So what would you tell about the expectation of 1 over x? What can you say about the expectation of e to the 1 over x plus 1? Remember, these are all functions of random variable. And what could be expectation of natural logarithm of square root of x? Okay, so the first thing to identify is what is our g of x, right? So g of x in this case is clear. It's 1 by x plus 1. Okay, and then we have to check few other things. For example, is it convex? Because to be able to apply Jensen's inequality, we need to check whether it's a convex function. So second derivative test we have to do. If it's always positive, then we are done. Then we immediately write the Jensen inequality, and that gives us the bound. Okay, the estimate of this. Okay, so in this case we are talking about like lower estimate. Okay, because the Jensen inequality is like greater than equal to. It doesn't tell us the other bound. Okay, so it will give us only one side bound. Okay, so let us see this. So let us use this space to solve for this. So what we had was to find x. So g of x we wrote. So g of x is 1 by x plus 1. Okay, and then let us do the derivative, right? So g prime of x is minus 1 by x plus 1. Okay, squared. Right, so this is the first derivative, and then the second derivative of this g prime of x is what? So this is x plus 1 minus 2 and then minus 1, right? So derivative of this will be minus 2 minus 1. So this will be plus 2 by x plus 1 minus 2 and then like so this will be like minus 3, right? So again minus 1 here. So this is what we know is the derivative of such things. Okay, so let us clean this up. So 2 by x plus 1 cube, right? So this is 2 by 1 plus x cube, but this is going to be positive because yeah, the range was assumed to be positive anyway. So this is for x greater than 0. This is greater than 0. Okay, so what does this imply? This implies G is convex. So G is convex on 0 infinity. Okay, then from Jensen's, so using Jensen, remember we don't say Jensen, okay, we call it Jensen because he was a Dutch guy. So J is silent there, okay. Not silent, but I mean, yeah, you can say silent. Yeah, you can say silent. Okay, so using Jensen's inequality. So using Jensen's inequality, what we know is that expectation of 1 by x plus 1 is greater than equal to, so what was that? Expectation of, so what we know is like the line joining the curve is above, right? So it's like expectation of the g of x. The curve, average of the curve value is greater than equal to the g of the average of the points. Okay, so this was the Jensen's inequality, right? So average expectation of this average of that is greater than equal to g of so g for us is so g of expectation of x, right? So let me write this one more step just that so that you have clarity. So now g of expectation of x. So in place of x, I have to put expectation of x, right? So this is 1 by expectation of x plus 1, right? So this is the estimate we have. So expectation of 1 by x plus 1 is going to be greater than equal to expectation of x plus 1. And where we given the expectation value? Yes, so this was 10. So it's 1 by 10 plus 1. It's 11, 1 by 11, right? Okay, so now let us, so B part would be similar, right? So B part, what do we have? We have expectation of 1 by x plus 1. So what we have to find is expectation e to the 1 by x plus 1, right? So here again, g of x, the function is g of x will be e to the 1 by x plus 1 now. So we are supposed to do the derivative of this. So what is the derivative of this? It's of the form, it's like a chain rule you have to apply, right? So it's like derivative of g prime of x is, first of all, you have to treat it as e to the u and then du by dx, right? So e to the u and then u is 1 by x plus 1 and e to the u and du by dx. So this is like minus 1 by x plus 1 squared, right? So okay, so again, like you can continue with this and then you may do the double derivative test and so on. But this seems to be a little bit more tedious here. But what I can derive a rule is the following. How do I see this, right? So I see this as a function of function, right? So let me say, what do I mean by this, right? So yeah, so I can treat one function as let h of x is e to the x, right? So let h of x be e to the x and g of x, let us say, is 1 over x plus 1. Okay, so this is tedious. Try something else. Okay, so what is the something else we are trying to say? We redefine g of x. You should not be confused with this. Okay, so what I'm trying to say is like I have this and okay, so what do we observe here? So observations here are the following. Hx actually is convex and also non-decreasing, right? So Hx is convex and non-decreasing. In this case, it's increasing. Okay. And then second observation that we have is g of x is convex, that we have found before also, right? So g of x is convex. Okay, so sometimes also write convex like this. Okay, so g of x is convex and hx is like this. Now the question is, the function that we are given is of the form fx is h of g of x, right? So h of g of x, which is the actual function that was given to us, right? Okay, so now the question is, if hx is convex and non-decreasing, gx is convex, what can you say about functions like this, right? So what can we say about the functions like this, right? So so what we know is the second derivative test also, right? So what will happen if we do the second derivative test on this? So first, fx is f prime x will be, what will be the f prime x using the chain rule, right? So the first will be h prime, and then like h prime of g and so on, and then g prime, right? So the prime here means the respective, so h is seen as a function of g, so h prime is like dh by dg. Okay, and when I write g prime, then it's like dg by dx, because g is seen as a function of x. Okay, so all right, so this is the first thing using chain rule. Chain rule of okay, and but we need a double derivative, right, for the double derivative test. So it will be like more here now. Okay, so let me do a little bit more in a clear way. So what this was, dh by dg and dg by dx, right? So f double derivative. So first, so there will be like two things now, right? Because dh by dg itself, this is guaranteed to be function of x, but this even after differentiating with this, okay, it still can remain yeah, function of x, and so it still remains function of, I mean, it is still a function of g, right? Okay, so and so g is again a function of x, right? Okay, so let us do first the product rule. So first function differentiation of second, and second function. So first function into differentiation of the second. Okay, and so first function into differentiation of the second will be, it will make it squared, right? Plus second into differentiation of the first, right? So differentiation of the first will be d2h by yeah, differentiation of the second will be d2h by dg squared, and then you will have one more term dg by dx because of the chain rule, right? Okay, so what I can do here is that I can remove this and do a square here. Okay, so this is the thing we have now. Okay, so what we have is h is convex, so the double derivative of h is going to be positive. Okay, and this guy is always positive anyway because it's a square, and g is known to be convex, so double derivative, according to double derivative test, g is going to be this, and this is non-negative, non-decreasing, right? So non-decreasing means that the first derivative is greater than or equal to 0. Okay, so this is because since h non-decreasing, okay, since h non-decreasing, and here since g is convex, here because h is convex, since h is convex, and here it's by observation, right? So obvious. So here, so what we know is that overall this is greater than or equal to 0. Okay, so here we use a slightly different route to claim that this is greater than or equal to 0. You could have gone in this way also. As I said, it could have been tedious but you may, again, because it is positive, you should be able to prove also that this will be positive if you go ahead and do one more derivative. But sometimes it's easier to use this. So this is a convex. So now we can do an estimate, right? So now so what was that? Expectation of g of x, right, is greater than or equal to expectation. So expectation of g of x in this case is 1, not 1, but e to the 1 by x plus 1 is greater than or equal to 1, sorry, again, e to the 1 by expectation of x plus 1. And then expectation value was 10, so 1 by e to the 11, right? So this is the bound that you have on this. And similarly, you can do the third one. Third one, I can leave it as an exercise. Okay, so now what I will do next is to define some two important theorems. This one is called law of large number, and another one is called central limit theorem. So these are theorems on sequence of random variables and how do they behave if I take n tends to infinity and so on. Okay, so central limit theorem is an interesting theorem, and earlier I told you that standard normal distribution is a very important distribution, and now you will see the reason why standard normal distribution is very important distribution, because any other distribution can be studied using standard normal distribution. Okay, that's a very powerful statement, right? So the probability values can be computed via that, especially if the number of samples you are taking is large. And to put it very bluntly, if I take many samples of any random distribution, right, in the limit as n tends to infinity, let us say n is the number of samples, then in the limit they will behave like a normal. Okay, so if you are taking a heights of students in a class, and if you have many, it's a very big class, let us say, then it will start behaving like a normal distribution. The height of the students will look like bell curves, in the sense that more and more students will have the average height, obviously. Okay, and then the extreme heights will be very short, people will be very less maybe, and very tall people will be very less. And this is true for any distribution. That's what it's trying to say. Okay, so we will see these two important theorems. So, but before that, we have to make some. We have to define a few things. So let us. First thing is the sample mean. So let x1, x2, xn be IID. Remember what was IID? Independent and identically distributed. So this we defined in the last class. So that would guarantee that each of these have the same expectations and variance. Okay, they are coming from same distribution and so on. So that was the definition of IID. Then the sample mean x bar, okay, that's how we define the sample mean, is defined as follows. This is how we define. So why do we call it sample mean? Because imagine a population. Population here means like you have a lot of data collection here, okay, but then from here you picked n samples. Okay, so these n samples could be your x1, x2, xn. Okay, samples, observations, whatever. Okay, so it could be like the heights of the students and so on. Okay, so n students. So you can pick some sample and then you take an average of that. So that is why it will be sample mean, because I'm taking some n of them from an even bigger data, let us say, and then I will define on my sample of n size, I will define a sample mean to be like that. So I just divide by n here. Okay, so it is easy to establish the following. expectation of the sample mean will be expectation of x. Okay, so that's kind of trivial, right? So expectation of x bar due to linearity and 1 by n will come out. Okay, so this is expectation of x1 plus dot 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 plus expectation of xn, right? Now we know that expectation of x1 is equal to expectation of x2 because they are all coming from the same distribution, is equal to expectation of xn, and this is let us say expectation of x, some representative x, okay, which have the same distribution. So we can write all this as equal to, so n times expectation of x, because there are n of these and divided by n. So this is expectation of x. Okay, so it's nothing but the sample mean. The expectation of the sample mean is the expectation of the underlying distribution that they all follow. Okay, so that was easy. And then similarly, we can prove that the variance of the sample mean is variance of x divided by n. Okay, I leave it up to you to establish this. Again, straightforward, because variance is also will also be variance of x1 plus variance of x2 and so on. Okay, so you can again establish this fact. Okay, so okay. So yeah, so here one thing to note is like 1 by n constant is there, right? So if you apply the variance, 1 by n square will come out, and then from the top you will get n of those variances. So that's why you will get n here. Okay, because variance of ax is a square variance of x. So this 1 by n is like a here, right? And so 1 by n square will come out, and then n will cancel from above. Okay. So now we are ready to state a weak law of large numbers. So let's see what does that mean. Let x1 to xn be id random variable with mean this. So this is their id. All of these, let us say, have the same mean mu. Then for any epsilon greater than 0, any small number epsilon greater than 0, we have the following. So what does this mean? It says that probability that the sample mean, okay, so this is the sample mean from the mean of these distributions, okay, and then if you take the absolute value of that, the probability of that happening is being greater than epsilon, and the probability of that happening is 0. Okay, that's what it's trying to say. In other words, in a very simple words, the sample mean will approach the mu with probability, high probability, with probability 1. Okay, so that's what it's trying to say, because this is any epsilon, right? So this means that I can make epsilon as close to 0 as possible. In other words, I'm saying that the probability of x bar being different from mu is going to be very, very small. Okay, because that being greater than 0, the difference of that being greater than 0 is going to be almost 0. Okay, the probability is going to be 0 as n tends to infinity. Okay, so that's what this result says. That so this result, what this says is like your sample mean will approach the true mean of the underlying distribution, because remember they are all coming from identical distribution and they do have some mean. So let us say they follow the mean of some underlying distribution x. Okay, and these were the samples that were taken from there. Okay, so they will so if you take a small value, maybe you will be a little bit far from the actual mean. If you take more and more, then you will approach the actual mean. Okay, so that's not really I mean, this is something intuitively we expect, right? So we expect this to happen, right? So we can like try to prove this. So assume that the variance of the underlying distribution x is sigma square is finite. Okay, sometimes finite is said to be like this, less than infinity. Then what do we have? Probability that x bar minus mu is greater than or equal to epsilon. Now we can apply the Chebyshev inequality. And if we do that, that told us that it's variance of x bar divided by epsilon square. Now variance of x bar is variance of x by n, right? So that's what we know for the sample mean, right? So that's something we proved previously. So this is same thing as saying variance of x by n epsilon square. So variance of x bar is variance of x by n. Okay, since okay, and now it is clear, right? Now if I take n tends to infinity, this guy is going to be 0. Okay, so this implies limit n tends to infinity p x bar minus nu greater than equal to epsilon tends to 0. Okay, or not tends to 0. Since we have already said its limit, now we will say equal to 0, right? Tending part is covered here, right? Okay, so this is what we have. So this is a law of large number and it follows easily from the Chebyshev inequality. Now we come to another very important theorem. It's called central limit theorem. Okay, so central limit theorem, I told you in the beginning, it's about things going to the all random variables in the limit behaves like a standard normal. Okay, so that was the statement. Okay, so let us consider again IID random variable with expected value mu, and which is finite, and then the variance is let us say sigma square. Then the random variable this. Okay, so this is defined in this way, right? So it's a kind of, we have standardized this. Okay, so we took the sample. Okay, we took the sample distribution. Okay, so it's like x1 plus x2 to x divided by xn, and then from there we subtracted the nu and then this, and all this scaling was done in a way to make sure that it becomes a standard normal distribution. Okay, so this thing converges in distribution to standard normal variable, standard normal random variable as n tends to infinity. Okay, so as n tends to infinity, this will behave like a standard normal variable in the sense that the mean will be 0, and then the variance will be 1, and the PDF will be like or the CDF will behave like the CDF of the standard normal. Okay, so this is what it's trying to say. So if you and so if you take yeah, so this is what we have. I think there is a mistake here. It should be Zn here. Okay, so as Zn as n tends to infinity, the Zn less than equal to x will be behaving like a phi x. Okay, so this is as if like Zn is behaving like a standard normal distribution, because the probability of that is being given by the standard normal distribution, right? So this is the CDF of standard normal, if you can remember standard normal. Okay, so in the limit, and we are not saying that just like that for n fixed. In the limit it will be, but even if n is not very large, you can expect that it's like good enough approximation. So that's why knowing standard normal is very good thing, because for samples with very large size, you can get the probability values using a standard normal itself. Although the distribution could have been anything, it could be binomial, it could be exponential, uniform, whatever distribution, it's independent of that, independent of what distribution you're talking about. Okay, so it does not matter what the distribution of xi is. If you define like this, so what are the steps you have, right? Someone will give you the distributions. You will form a quantity like this, right? So you will form a quantity like this, and then you may work. You may find the probability values like this. Then xi can be here. The xi can be discrete, continuous, mixed. Okay, it doesn't matter what the nature of the random variable is. It could be any. Okay, the same result holds. Okay, so just to give you an example of what is happening with this. So xi can be any distribution. Let us say it's Bernoulli. Okay, then we know that for Bernoulli expectation is p, and the variance is p1 minus p, And if we also know that if we add the Bernoulli, so each Bernoulli trials are independent. So it's like a coin toss, each of them are independent. Then if we sum them, then we know that sum of independent Bernoulli is nothing but binomial. So that also results we have proved before. And hence, if you form a quantity like this, okay, if you form a quantity like this, so you form a random variable Zn like this, so Yn is known to you, which is the sum of this, and then you subtract by this, and then you do like this. Then the figure on the right shows the PMF of Zn for different values of n. So here you will appreciate what is happening as the Z as the n value is increasing, right? So this is 1. This is not really normal, standard normal, right? No way, right? But here you see that, okay, this is like this. Maybe you can say that it's still not like a bell curve. Here you are seeing some pattern, okay? So again, but if you go ahead and do it for Z30, so you can plot these results, let us say in MATLAB, then eventually you start seeing like a very nice bell curve. Okay, so this is the familiar bell curve associated with standard normal distribution. This is the PMF. And as n tends to infinity, you will approach the continuous bell curve, which is exactly symmetric about the origin and so on. Okay, so you started with Bernoulli, and then you plotted the PMF. So these plots can be done with Python library and so on. So I leave it up to you to play with this, and it approaches the bell curve. Similarly, if I take a uniform random variable 0, 1, the expectation is this, in this case is half, and then the variance is and the variance is like 1/12, and hence if we define the Zn to be like this, and then the figure on the right shows the PMF of Z. So you started with normal distribution that looks like this. So if you took two of this, then it looks like this. If you took 3 of this, then it is looking like this. And then if you took 30 of this, distribution we are given, if we form a quantity like this, provided, so since we are, so assuming that these are known distributions, so from there we can get a random variable in the limit that is very much like a standard normal. And the advantage of this is that for standard normal, let us say all the tables and all these are given to me. So from there I can calculate any value. And the very important thing is like this could be any, basically any distribution, right? So that's the most important point. So write the random variable. So what are the steps? How to apply the central limit theorem? Okay, so what are the practicalities of this? So well, given that you are working with the data and they all follow some distribution that you don't know even. Okay, you maybe or if you know, let us, if you know, but you only know, let us say, expectation and variance and so on, you don't have a hold of the PDF. Okay, if that is the case, then what will you do, right? To apply the central limit theorem, then you will take a sum like this, and then let us say mu is known. Let us say mu is known. Then expectation of y you know will be this. Variance of y you know will be this. So from the CLT, you will form a quantity like this, y minus epsilon y divided by this, and this will be this. And what this CLT guarantees that this will be approximately standard normal. And hence, now if you are supposed to compute the probabilities of y, it could be computed using the standard normal data. So for instance, probability that the y lies between between y1 and y2. So I do the rescaling, right? So I subtract minus n mu and divide by square root of n sigma. I do this on all sides, so hence the inequality doesn't change. Okay, so this is what happens. So this and this is the same thing. I just subtracted and divided by the positive quantities. And then because this is standard normal, so this is standard normal approximately. Okay, so that's why we have this not equality but approximately equal. And then for standard normal distribution with A1 and A2 A and B bounds, we know that it is computed like this. So probability value is phi of B minus phi of A, right? So that's the advantage of using using this. So let us see some application of central limit theorem in practice. Okay, so this is an application. So a bank teller serves customers standing in a queue one by one. So there is a bank teller, and then customers go one by one. Okay, they are in a queue. Suppose that the service time xi for customer I has the mean expectation of xi is 2. Okay, so each customer on average spends 2 minutes. Okay, and then let us say the variance of this random variable xi is 1. We assume that the service times for different bank customers are independent. Okay, so we also assume that these are independent. So we are essentially assuming they are IID because they have the same mean and variance, and then and they are independent also. So we have put in the assumptions that are needed for IID. Let y be the total time the bank teller spends serving 50 customers. Okay, so y is the total time. So obviously we are getting into the precise formulation. So y is sum of xi's, right? That will give us the total time. Okay, the bank teller spends serving 50 customers. So 50 n here is 50. Find the probability that y is greater than 90 and less than equal to 100, right? Okay, so so we can try to solve this here. So we have, so first of all, y is nothing but sum of the, because it's the sum of the times, right? So plus xn, where n is 50, and we were already given expectation xi, and this was mu, and on average they were spending 2 minutes each, and variance of xi, so it's like the varying time that one spends, right, is like sigma square, which was given to be 1. Okay, so these are given quantities. Okay, and now we are supposed to compute the probability values that the sum of the times lies between 190 minutes and 110 minutes. So this will be the probability. So what was that? So this will be probability that, and so how were we? What was the formula we were given? This one, right? Y minus n times mu divided by, so y1 minus n, so 90 minus 50 times 2, right? So something like that, right? And divided by square root of n, which is 50, square root of 50, and then sigma is 1, right? So it's like 90 minus, yeah, 90 minus n mu, right? So n is 50 and mu is 2, right? Yeah, let us try to do this. So let me check, I forgot already. So what was this? So y1 minus n mu by square root of n sigma. Oh, sorry, actually we should, isn't that we should look here, but there is no change anyway, right? Yeah, so we should look here because we will be computing this with respect to phi. The first step will be anyway this, right? So yeah, so y1 minus n mu divided by square root of n sigma. So y1 minus n mu divided by square root of n times sigma less than, and then y minus n nu divided by square root of n sigma is less than. Okay, and then now we have y2, right? So y2 minus n mu divided by square root of n times sigma, right? Okay. Okay, so what do we have here, right? So what is here? So this is probability that okay, so 50, so it's 100 and minus 10, right? So minus 10 by square root of 50 less than, and then y minus n mu, I just keep it for the moment, and then 100. So it's like 10 here, right? And then divided by square root of 50. Okay, so now what I can do is I can estimate these values using phi, right? Yeah, so I know that I can estimate these values using phi. So this will be phi of so this will be phi of, yeah, so this quantity b minus a, right? So this is like 10 by square root of 50 minus phi of minus 10 by square root of 50. Yeah, so so this is what I get for by using CLT. I can actually have an estimate on this on this quantity, right? Okay. Do we have some more example on this? Yes, we have some time also. Okay. Similarly, like we can also try to solve this example. For instance, here, if in a communication system, each data packet consists of 1000 bits. Due to the noise, each bit may be received in error with probability 0.1. It is assumed bit errors occur independently. Find the probability that there are more than 120 errors in a certain data packet. Again, the problem is again the same because the random variable y will be again sum of x1 to xn, and so the way we will model this is like each bit, right? So I will take xi. So xi, let us say, is the random variable for the ith bit. Okay, so if then it's about what is the probability with which I receive an error in the xi bit. Okay, so let us say xi equal to 1 if the ith bit is received, and let us say xi is 0 if 0 otherwise. Okay. Okay, that's how we model it. And so here xi's are IID. So xi's are IID. In fact, xi can be modeled as Bernoulli. Okay, so Bernoulli with p is equal to, oh, it is given to us is 0.1, right? Okay, and so I find the probability that there are 120 errors in a certain data. So again, I will define this to be x1 plus x2 plus xn. And then in this case, the expectation of xi is mu, which is p, which is 0.1, and variance of xi, which is rho square, is p1 minus p, which in this case is 0.09. Okay. Now using CLT, what we have is there are more than 120 errors. What to find the probability? The probability that y is greater than 120, okay, is the same thing as, okay, sorry. So if the y is greater than 120 is the same thing as probability that y, so I can scale, right? The trick is like to scale it accordingly. So y minus n nu divided by square root of n sigma The standard deviation is, so the same thing I will do here, right? So 120 minus n nu divided by square root of n sigma. Okay, so now it becomes a standard normal. Okay, now it becomes a standard normal. So I will apply. So this is 1 minus probability that y minus n nu by square root of n sigma is less than equal to 120 minus n nu by square root of n sigma. And now I know what is this, right? So this is for the standard normal, because this is standard normal. Standard normal. So from here I can write 1 minus and then phi of this guy. Okay. Yeah, that's correct, right? Okay, yeah. So phi of so 120 minus n. So 120 minus n nu, right? So nu is 0.1 and n was 1000, right? So 120 minus n was 1000 times nu is 0.1 divided by square root of n. N is 1000, right? Okay, so there is some, we cannot have an exact square root here. And then sigma was the standard deviation, right? So that's a square root of this guy. Okay, so I think you can figure out this. Okay, so this is the calculation that we are left to do, and we can leave it here, right? Okay, so again, using the CLT, we could find the probability of this. The trick is to scale it, and then we get this. You may wonder, like, we are getting, but no, we are starting from here, right? So this is just intermediate step, and then we make it standard normal, do the appropriate scaling, and then we get the answer. So, and same thing also happens in the previous example. We started from here. This was the probability we were supposed to find. And this is equal to the proper scaling we did and so on. And then we made it into this. And the original question did ask for us. And we follow the equality and we arrive here. Okay. So, so we are indeed computing probability for the y by transforming this into this form, where we get a standard normal distribution. So this is where I think I am going to stop, and we will continue with this. So this part is done. Now we will start statistical inference, and we will do classical inference and then Bayesian inference. The overview. Okay, so these are the topics you study in detail also in later courses. So inference part is the last topic left, and that's very easy part. Okay, very easy part is left now. So okay, with this I will stop. Okay, so have a nice day and bye. If you have doubts, you should obviously ask. Okay, I don't have to tell also. So you should ask all the time, or me or TA, whoever you find comfortable. Okay. Okay then, bye.